In the last lecture, we learnt about the structure of a transistor and something about its working. We also saw the symbol for the NPN and the PNP transistor. How do you recognize one from the other? By the arrow. If this arrow points outwards, if the emitter arrow points outwards, it is an NPN transistor. If it points inwards, then it is a PNP transistor. So, we shall continue with this study of the working of the transistor, how it works as an amplifier and what properties it has as an amplifier. But before that, we must learn of the characteristics of a transistor. So, the input characteristics, for the input characteristics we plot IB against VBE. You remember, IB is the current going to the base, it is the emitter base current, and IC is the current going through the collector, it is the emitter collector current, and VBE is the bias, VBE is the bias between the base and the emitter. And so, we plot IB against VBE, the current against the voltage between the base and emitter. These are the input characteristics. For output characteristics, we are on this side now. We plot IC against this potential difference. This is VCE. So, we plot against this potential difference. So, let us first see the input characteristics. IB in microamperes against, you remember that base current is really very small, base emitter current is really very small, and therefore, it is measured in microamperes, and this is the VBE, the bias between the base and emitter. And if I plot IB against VBE, then this is the kind of curves that we get. This is for one constant value of VCE, this is for another constant value of VCE. And what do we get from this input characteristics? We get the input resistance. How do you define the input resistance? It is d delta of VBE by delta of IB, that is a small change in VBE divided by a small change in IB. So, suppose we take this curve for VCE1, then if we have these 2 points, then VBE is this and IB is this. So, if we divide delta VBE by delta IB, then we get the input resistance. For output characteristics, the circuit remains the same, but we now plot, as I said, IC against VCE. So, we shall plot IC against VCE. So, this is IC on this axis and this is VCE on this axis. And for constant IB, for constant base currents, this is the kind of graphs that we get. These are the curves for constant IB. IB increases this way, IB1, IB2, they increases this way. This is constant IB currents. For each curve, IB is constant, and we plot IC against VCE. And then we draw a line. This is known as DC load line, and this is from IC maximum, that is this, to the point where VCE is equal to VCC. This is VCC and VCE is equal to VCC, that means there is no resistance here, and this is the from maximum IC to maximum VCE, and this is the line. This is known as the DC load line, and all points where they intersect these curves are the operating points for the transistor. But the most important of these operating points is somewhere in the middle, called Q point or quiescent point. Why is it chosen in the middle? I will show you in the next slide. You see, it is chosen in the middle so that the input signal is not distorted. Suppose we had chosen here the operating point, then what would happen? This part will be all right, but this part would be chopped off. So, the input signal would be disturbed. Here, similarly, if the Q point is here, then this part will be all right, but this part will be cut off. So, again the output signal will also be affected if the Q point is not somewhere in the middle. If the Q point is in the middle, then input signal is in proper shape and output signal is also in proper shape. and they are not disturbed because the Q point is somewhere in the middle. If Q point is here, then this as well as this, both or one of these could be affected, the shape would be affected. So, we choose the Q point somewhere in the middle. So, that is the operative part, that from the output characteristics we draw this load line and choose the operating point somewhere in the middle, and the change in the current, in the collector current, to change in the base current, this ratio is called beta. This is the current gain, the ratio of how much change produces how much change in IC, how much change in the IB produces how much change in the IC. The change in the IC is much more than the change for the same change in IB, and this ratio is called beta, and this is called the current gain of the transistor. The same circuit that we used for the input output characteristics can be used for transfer characteristics. That is, from we will take one parameter on this side, one parameter on this side. They are known as transfer characteristics. And what do we plot? We plot the output voltage against the input voltage. So, to that, what is input voltage and what is the output voltage? You remember, VBB, this VBB is equal to IBRB and the VBE. If you use the Kirchhoff's laws, then VBB is IBRB plus VBE, and VCE similarly is equal to VCC minus ICRC. So, these are the two equations, and VCE or VBE can be taken as the input voltage and VCE can be taken as the output voltage. So, we shall plot output voltage against the input voltage. So, in this circuit, VBB supplies the voltage to the base. It can be considered as the input voltage Vi. So, VBB is the input voltage. VCE is the voltage that develops across the collector emitter circuit. It is the output voltage V0 or VO. The VCE is the one that develops across this emitter collector circuit, and therefore, that is the output voltage. So, we plot output voltage against the input voltage. The curve can be conveniently divided into three regions: this region, and this region. In this region, there is hardly any current. It is a cut off region, because the potential difference is not able to overcome the potential barrier in the junction and in the emitter base junction. So, there is hardly any current. Here the current has become maximum, and therefore, there is no change in the current. So, this is saturation region, this is cut off region, and in between is the active region. In the active region, it is the active region that we use the transistor for amplifying purposes. Here it is sort of switch off, there is no current. So, the transistor acts as switch in the off position. Here again there is no change in the current. So, it is in the fully on position, the current is maximum, but there is no change in the current. So, this again a switch, and this switch is in the saturation region, this switch is in the on position, this switch is in the off position, and in this region, which is almost linear, we have the active region, in which region the transistor functions as an amplifier. And as I said, we plot V0 against Vi. V0 is VCC minus ICRC, implies that V0 falls rapidly. It falls rapidly, the fall is linear and continues till V0 reaches a near 0 value. At this stage, the collector current reaches its saturated value. So, these are the transfer characteristics. Transfer, because the output is plotted against the input, output voltage is plotted against the input voltage. So, and this again let me repeat, there are three regions in this. This is almost 0 current, this is the maximum current, but there is no change of current here, there is no change of current here. So, the transistor acts as a switch in the off position in this case, and in the on position in this case. Here in this region called the active region, the transistor will work as an amplifier. And what is an amplifier? Which amplifies output with respect to the input. So, delta V0 would be larger than delta Vi. This ratio gives us the voltage gain, how much Vi has been enhanced to get Vo. So, this ratio Vo by Vi, delta Vo by delta Vi, that gives us the voltage gain of the transistor, and therefore, this region is the region where the transistor acts as amplifier. Three regions of the transfer characteristics are self-explanatory. I have explained to you already. So, let us come to what is known as common base amplifier. As I said, base is common to both input as well as output, and this is a circuit. This is the input signal and this is the resistance in the emitter circuit. This is the voltage VEE and this is VCC, this is RC and this is the output across the load resistor. So, this is a circuit, this is again NPN, remember this symbol, arrow going out. So, this is NPN again. So, this NPN common base amplifier circuit. Remember, this is reverse bias, therefore, the output resistance is quite high. This is reverse bias, this is forward biased, always emitter base is always forward biased. So, this has very little resistance, this has very high resistance, and the voltage gain is almost unity. There is not much in terms of voltage gain. However, this has a low resistance, this has a high resistance. Input is low resistance, output is high resistance. Therefore, this amplifier can be used for matching impedances. For example, you have to transfer power from a device which has low resistance to a device which has high resistance. So, what do? If you just put them together, the power transfer is not very efficient. However, if we put some such device in between, the input connected here and the output connected here, input of the device from which power is to be transferred to the output to which the power is transferred. If in between we put this common base amplifier, then the transfer of power from the active device to another device is much more efficient, because there is impedance matching. The device has low impedance, this also has low impedance, the device to which the power is to be transferred has high impedance, this also has high impedance. So, if we connect them in this fashion, then there is impedance matching, and this impedance matching ensures the transfer which is very efficient. This is all explained here. The impedance matching is a technique which effects efficient transfer of power from an active source to an external device. Suppose power is to be delivered from a source whose output impedance is low to a device whose input impedance is high. To maximize the transfer of power, in this case a common base amplifier is inserted between the two. See, this active device has low output resistance, and this device to which the power is to be transferred has high input resistance. So, to match them, we low output, low input, so matching. High output and low input of the device to which the power is to be transferred, against there is matching. So, by impedance matching we effect the most efficient power transfer, and that is the use of this common base amplifier. As I said, voltage gain AV is delta V out by delta V in, and this can be written as delta IC, that is output current, into the output resistance, and this input current to the input resistance, and this delta IC by delta IE is called alpha. The current gain delta IC by delta IE of the common base amplifier is called alpha. The current gain delta IC by delta IE, and there is a ratio of the output resistance and the input resistance is called R. So, the voltage gain is alpha times R, where alpha is the current gain. R is the ratio of the output resistance to the input resistance. The parameter alpha is also denoted by, sometimes in some books at a higher level, it is denoted by HFB. The combination of voltage gain and the suitability for impedance matching dictates the use of common base amplifier in electronic circuits. That is, the combination voltage gain is not very much, but the suitability for impedance matching, if the output impedance of an active device is low and the input impedance of the device to which the power is to be transferred is high, then we use in between the common base amplifier for impedance matching. Let us now look at common emitter amplifier. Common emitter amplifier, as I said, is the most important one of all these. Why is it so? Because of one reason is the phase difference between the input and the output. Phase difference, input is like this, output is like this. That the phase difference of 180 degrees or pi between the input and the output. And this is the circuit for the common emitter amplifier. This just explains the use of this block diagram for the transistor. Otherwise, this is the emitter, this is the collector, this is the base, and this is forward bias, this is the reverse bias, nothing much. And these are the voltages VBB, VCC, and this is the output across this VCE, as we have been saying. So, this is the common emitter amplifier. The common emitter amplifier is more popular than the other amplifier configurations, because it has a good combination of current gain and the voltage gain. The output may be taken across VCC and RL as shown here, or simply across the load resistor. In some books you might find the output taken across the load resistor. Does not matter, the phase difference will still be there. So, sometimes you take the output here, sometimes you will take the output across this resistor, it does not matter. In both cases the output will be in opposite phase to the input, as explained below. Note that V0 is VCE. We have been saying this all along, that output is VCE, output voltage is VCE, which is VCC minus ICRL. This is RL, ICRL. So, IC times RL, and this is a loop, and you can apply the loop Kirchhoff law, and you will get this V0 or VCE is equal to VCC minus ICRL. When the input signal turns positive, suppose we take the positive part of the signal, the forward bias applied to the emitter increases. You see, this is in the same direction as VBB. So, the forward bias increases. If the forward bias increases, then it sends a large number of electrons from the emitter to the collector, from the emitter to the collector. A large number of electrons are sent, and if large number of electrons are pushed to the collector, increasing IC, as a result VO decreases, because VO is this, which is VCC minus ICRL. If IC increases, then this term increases, and therefore VCE decreases, so output decreases. As a result, VO decreases, making it out of phase by 180 degrees with the input signal. You see, we increase the input signal and the output voltage becomes lower. Therefore, there is a phase difference of 180 degrees or a phase difference of pi between the input and the output. Voltage across RL is minus ICRL, again out of phase with the input. That is, if you want to take the output across this load resistor, even then there is a phase difference of pi between the input and the output. The current gain is defined as delta IC by delta IB. Delta IC, change in the output current to the change in the input current. So, delta IC by delta IB. A transistor is usually designed to have a high beta value. Beta is delta IC by delta IB, and as I said earlier also and several times, that all these transistors are designed for a certain function, for a certain purpose. So, the transistors are so designed that they have a high beta value, that is, the current gain is very high. The voltage gain is current gain into the ratio of resistances. So, it is beta R, where R is the ratio of the output resistance to the input resistance, and the power gain is beta times current times the voltage gain. So, it is beta squared R. So, we have all the formulae here, the current gain, the voltage gain, and the power gain. Current gain is delta IC by delta IB, designed to be very high. Then voltage gain again is quite high, because beta is there times the ratio of R out and R in, and power gain is a beta times AV. So, it is beta squared R. Look again at the CE circuit, common emitter circuit. Using Kirchhoff's laws, as I explained to you earlier also, we get IE equal to IB plus IC. You see, consider this a loop or a point junction for the Kirchhoff's law, current law. Then these two currents are going in, this one is coming out. So, IE is equal to IB plus IC. So, IE is equal to IB plus IC, and now you divide by delta IB, delta IE by delta IB, that is equal to 1, delta IB by delta IB 1, and delta IC by delta IB here. The left hand side can be written as is delta IE by delta IC into delta IC by delta IB, and this is 1 plus delta IC by delta IB. Using now the definitions of alpha, alpha is delta IC by delta IE. So, it is 1 by alpha here, and delta IC by delta IB is beta, and then 1 plus once again delta IC by delta IB beta. So, you can play around with alpha and beta, and you will get the relation alpha is equal to beta by beta plus 1, or beta is equal to alpha by 1 minus alpha. Whichever relations you want to use, you will get from this equation. Suppose according to the manufacturer, a transistor has parameter alpha equal to 0.95, alpha is 0.95. So, this is 0.95 by 0.05, so beta is 19. So, the current gain is 19. Remember that the common emitter amplifier is an inverting amplifier. Why is it inverting? Because the output is in a phase opposite to the input. Therefore, it is inverting amplifier. Whatever is positive in the input becomes negative in the output. So, it inverts in that sense. So, because the output is 180 degrees out of phase with the input. So, in this lecture we have seen two times. First of all, we saw the input characteristics, output characteristics, and then transfer characteristics. And then we discussed the working of a common base amplifier. A common base amplifier is used as impedance matching device between the device from which the power is to be transferred to the device to which the power is transferred. So, between these two we have this common base amplifier for the purpose of matching impedances, and common emitter amplifier is used in many other places, in many other purposes. It is more popular than the common base and the common collector amplifier. So, in the next lecture we shall study common collector amplifier and the important concept of feedback in electronic systems, and we shall see that the feedback can be positive as well as negative. So, the positive and negative feedbacks, and we shall use where positive feedback is used and where negative feedback is used. We shall discuss all that in the next lecture.